Hello, my name is Sunwoo Kim, and this is my report for Lab 4. This report will consist of the introduction, fundamental principles, experiment, computational model, results and discussion, and the conclusion. This lab is called Magnetic Braking with Faraday. The experiment consists of timing a bar magnet falling through a conductive tube of aluminum foil. In GlowScript, we will model the interaction between the magnet and the tube. When the magnet is falling through, it induces a current in the tube. This induced current exerts a force back on the magnet to oppose its fall. The purpose is to observe how this affects the time it takes for the magnet to fall through. Here's a summary of our results. The observed time it took was 1.01 seconds, and the computed time was 2.192 seconds. Here are the key principles we will be using today. The Biot-Savart law describes the magnetic field produced by a steady electrical current. It is mu naught over 4 pi times qv cross r hat divided by r squared. Faraday's law states that a changing magnetic field induces a voltage in a conductor. The equation is mf equals negative n, which is the number of rings, times the time derivative of magnetic flux. The minus sign comes from Lenz's law. Newton's second and third laws have to do with forces, and the second law can be manipulated to get the velocity and position update formulas as shown. So for the experiment, we are dropping a bar magnet through a conductive aluminum foil tube and timing how long it takes. Assumptions are that the air resistance and friction are negligible and that the bar magnet acts as a magnetic dipole. The system is the bar magnet and tube, and the surroundings are the Earth. I timed 5 separate trials and then found the average, which ended up being 1.0098 seconds. And then to the right are the properties of the tube and the magnet that I measured, and the magnetic dipole moment, 2.947, was found in Lab 2. Now we are moving on to the coding, and these are the initial conditions that I put in. We have our 3 constants, and the properties of the tube and the bar magnet, and time and the velocity of the bar magnet start at 0. Here is some of the code, the first part depicting the tube as a series of rings stacked on top of each other, and the next part visualizes the bar magnet as a cylinder. The last part shows a function created to calculate the magnetic field of a dipole and a function to calculate the time derivative of magnetic flux through each ring due to the bar magnet falling. And here's the rest of our code, starting with a simulation loop that occurs while the bar magnet falls through the tube. We used Faraday's law to calculate the current induced in each ring by the magnet, and Biot-Savart law to calculate the magnetic force on each ring due to the magnet. Newton's third law was used to then calculate the magnetic force back on the magnet due to the current carrying rings. Then net force on the magnet was calculated by including the gravitational force, and lastly our velocity and position update formulas were used to make our simulation proceed. This is the output from our code showing the magnet falling through the tube. The red shows a counterclockwise current while the blue shows a clockwise current. If we flipped the magnet, it would still fall the same way, but the directions of the currents would be flipped. The flat region of the velocity versus time graph to the right depicts the magnetic braking portion, where net force equals 0 due to the magnetic force canceling out the gravitational force on the magnet when inside the conductive tube. When net force equals 0, Newton's second law shows that acceleration will also equal 0, hence the constant velocity observed. Our observed time from earlier was 1.0098 seconds, but the computed time we got was 2.192 seconds. They're quite different, and this can be due to various sources of error. One possible source of error is the fact that in real life there are likely other forces like friction and air resistance that are not negligible and affect the experiment. Also, there may have been errors when starting and stopping a stopwatch, measuring properties of the tube or the magnet, and calculating the magnetic dipole moment. To conclude this report, we will cover some what-if questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Ohm's law shows that resistance is inversely proportionate to the induced current. With near zero resistance, the current induced in the tube would be very high. Subsequently, the opposing magnetic force on the magnet would also be higher, causing the magnet to fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be fewer total rings of current in the tube, reducing the force that they exert on the magnet and allowing it to fall faster instead.